All right, stats people, welcome back. We're at a part in the unit where we shift. You'll notice in the title of this section, we're not talking about proportions. Everything up until this point of the unit has been all about proportions. I don't do the exact same sequence the author does. I like to do all the proportions and all the difference in proportions, all the confidence intervals with proportions, all the hypothesis tests with proportions first, so you get really good, really comfortable and consistent with those formulas. And then all of a sudden we shift to a different set of formulas. Now we're going to talk about means, and then eventually difference in means and confidence intervals, hypothesis testing with means. So, so the formulas will look different today. It's very important not to be using the old formulas because they won't make sense, they won't work. You know all about this one here, finding standard error for proportions for p, where you do that p times 1 minus p, you divide it by n, you take the square root. There's another formula for means. It's still got a square root in it, still got an n in it, but you can't have a p because if you're talking about means, you're talking about x bar or x, or sorry, mu in some way, shape, or form. So, so there's there has to be something different. So here's what it looks like. It's very similar in terms of the square root going on here. And this is one format, but I could write this in a different format. So you get sigma, which is your standard deviation of the entire sample, divided by your sample size, square rooted. That's the idea. Now, got a couple follow-up questions that go with this. For a person collecting and analyzing statistics, in other words, sample statistics, which of these values, which of these two is hard for them to get? Now, it's easy for them to get this. This is just the number of samples. I may have said this wrong a minute ago. This is your population standard deviation. That's impossible to get because you're only taking a small, sample of the entire population. So that's going to be very, very tricky and, in fact, impossible. So we've got to have some other way to deal with that. So we'll talk about that eventually. Second part of this little follow-up, it says, just asking you to think about this formula. It's very similar to what happens in this formula, the previous one. What happens if you're able to increase the sample size? In other words, you make n bigger and bigger and bigger and bigger and bigger and bigger. Think about what this quotient becomes. If I were to make this 1,000,000 or 10 million samples, the bigger this denominator gets, the smaller this value will get, the smaller the standard error get, which makes sense. We've been talking about that all year. You're going to decrease standard error, which is what you want to do. You want to get as many samples as is practical if you're running a study so that you can decrease error, so you can limit the amount of error in the distribution. It also would make the distribution a little bit more narrow, the curve of that distribution more narrow, centered around the actual population mean in this case. Hopefully that makes sense. So we're going to use that formula real quick here in the first example. This is statistics from the Bureau of Labor Statistics. This is an actual thing that exists in the U.S. government. This is, many of you probably want to be statisticians when you're older. Well, if you do, the mean salary back in 2009 was $75,220. So they're making pretty good money. Good career for y'all to look into. Standard deviation of those salaries was 32,000. This is actual data. This is not made up. So sketch a possible distribution curve. This is kind of just getting us to go back to, what would that curve look like? We think it would probably look normalish, something like that. If I was in class, I'd ask you, where would it be centered? Where would that distribution be centered of all those? Probably be centered somewhere close to the mean, somewhere close to 75,000. And then we talk about, how much data falls in between these two limits here. Where would 95% of the data fall might be a more direct way to ask that. Well, probably within 2 standard deviations. So if you double the standard deviation that we had here, you might get that. Now, this is the standard deviation of that population. That's not the standard error of a sampling distribution. So I've got to use that formula. I'm not going to double this. I'm going to use that formula we talked about to find standard error. Hopefully that makes sense. I'm going to take that 32,000. I'm going to divide it by the square root of 100, because in this one I have 100 samples, which is 10. Hopefully that makes sense where the 10 comes from. So in fact, I'm not using 32,000. I'm using 3,200. Again, I'm using the formula for standard error to figure out how many standard deviations away I would be. And if I double that, it gives me 2 standard deviations right, 2 standard deviations left. And of course, you know it's be around 81,000 would be the upper limit. 68,000, almost 69,000 would be the lower limit. And again, those two limits would be like limits of a 95% confidence interval if I was going to construct a 95% confidence interval for this data, this statistics. And then there's a part B to this. What if you have 4 times as many statisticians that you've sampled? So you don't have the entire population, you have 400, 4 times as many. So same idea, you got 3,200. We think this is going to become narrower because we have a larger sample size. It should be a narrower curve than it was a minute ago. How much more narrow? Is it 4 times as narrow? In fact, you'll find out it's actually twice as narrow or half as wide because you're now taking 3,200 and dividing it by the square root of 400. What's the square root of 400? Well, that's 20. So, if you make this 4 times as big, it'll make your distribution half as wide. If you were to make this 9 times as big, it would make it a third as wide. If you make it 25 times as big, it would make it 1/5 as wide because the sampling size is square root relationship. So my standard error in this case would be 1,600. And again, if I'm thinking about 95% confidence intervals, if I double it, it gives me about how much is over here in the upper limit. If I double it and subtract, it gives me the lower limit. So if I add 3,200 onto that, it gives me, 78,000, a little higher than that. Subtract it, I get around 72,000. Hopefully that makes sense. Those values make sense. It's just using that new formula where you take the standard deviation of the population divided by square root of n to get your sampling error. So that's what this distribution could look like. So as I mentioned a minute ago, typically you're not gonna have all the population data here. You're not gonna know this standard deviation in a realistic setting. So there's got to be some way to estimate that standard deviation using the standard deviation of the original sample. Okay, so you're using S, the standard deviation of the original sample, instead, because you don't have the standard deviation of the entire population. If you had that, you wouldn't have to do this process. You'd already know everything about the entire data set. I'm going to pause this and go to next part here in a minute. I'll be back in part 2.